All right, so it's been a while since we've had a focus activity because we've been using the happy minutes at the beginning of the 6 weeks. But going back and revisiting an aspect of rational functions is going to help us with an idea today that we've mentioned earlier, converging or diverging. If a limit exists, if a sequence approaches a specific number, well, then we say it converges. If it does not approach a specific number, then we say it diverges. And actually looking at rational functions is going to be really useful to us. We want to figure out, does it have a horizontal asymptote or an oblique asymptote? Basically, we want to know what happens, the limit, as x approaches infinity. All right. So we brought this up the other day, but we didn't talk about it in a whole lot of detail. What was the one thing I looked at that helped me decide horizontal or slant? The degrees. And remember, the degree is the largest power that an expression has. So we're comparing the numerator to the denominator. So, for example, number 1 divided by 3x squared plus 3x minus 18. Now, the degree of the denominator is what? Okay, it is 2. Now, the degree of a numerical number isn't said to have a degree. So you're absolutely right. The degree of the denominator is larger. What do we do in that case? It equals 0. If the degree of the denominator is larger, it is the x-axis. That's where your asymptote is. So I know this would have a horizontal asymptote. It'd be y equals 0. Now, if I were to write it as a limit statement, the limit as x approaches infinity. Now, normally you'd go ahead and write the whole function, but that's quite a lot to write. So I'm just going to go ahead and say f of x is equal to 0. Because this would approach a specific number, I would say that this converges. It has to approach a single number. Okay, if it does not, then we say it diverges. Okay, just kind of think about the values of x going to infinity. That's the term number. The value of y that corresponds, that would be the sequence that's created. Okay. All right, well, let's try number 2. What do you notice about the degrees here? They're exactly the same. What do we do if the degrees are the same? Is that horizontal or slant? It's a horizontal again, so what do I do? There you go. So we have 1 and 1. They're the same degree, so you divide the leading coefficients. Okay. So 1 divided by 1 would just give me 1. Okay. So if I were to write out the limit statement, the limit as x approaches infinity, and that's small enough, I'll write it out, of x minus 2 over x minus 4 equals 1. So what would you say about this one? Would you say that it converges or diverges? I would say it converges. It does approach a specific number. The limit does exist. Okay. Well, let's try number 3. X cubed minus 9x over 3x squared minus 6x minus 9. Now this one's different. This one, the numerator's degree is larger than the denominator's. So horizontal or slant? This is a slant or an oblique asymptote. So how would I find it? You'd have to use long division. And actually, we didn't talk about this when I first showed you, but you can use synthetic division if your divisor is a trinomial. And the other 2 classes said they would want to see it. Would you guys at some point like me to show you that? It's a little more involved, but it can be done. So I'll try to put something together for that. So just for the sake of time, I already this morning went ahead and did the long division. Okay. So I'll give you a second if anybody's interested in writing that down. If you are, great. If not, I'm not too worried about it. But are there any questions about how I got the value here? The slant asymptote being 1/3 x plus 2/3? Okay. Now here's my question. I'm going to write this as a limit statement, right? So I'm going to come back up here. So I'm going to go ahead and say the limit as x approaches infinity of f of x, again, because I don't want to write that whole thing. Well, as x continually gets larger and larger, what are the y values going to do? They're going to increase. They're going to get closer to that line, but the value of y is going to continue to get larger and larger. It's going to increase without bound. So I would say it equals infinity because you're approaching that line, which just goes up forever. It's at a slant. It's got a positive slope. Now, here's the thing. Does infinity represent a specific number? No. So in this case, would you say it converges or diverges? This one would diverge. Okay. It does not approach a specific number. Okay, well, what about 4? X squared plus x minus 6 over negative 4x squared minus 16x minus 12. The same or different degrees? They're the same. So that means a horizontal asymptote. If they're the same, what was that trick again? I don't remember. Divide the leading coefficients. Okay, so I can say the limit as x approaches infinity of f of x, what is that limit? Negative 1/4. There you go. So what would you say if you had to classify this one? Converges or diverges? Converges. If it approaches a specific number, it converges. If it does not, then it diverges. Okay. So it's actually been a while. Is that starting to come back to you? You remember when we spent the time talking about all the different discontinuities, the infinite, the removable, we found the roots, all that kind of sound familiar? So if I were to give you any one of these right here and ask you to go ahead and graph it, we could do it like that? Okay, maybe a little bit of practice. Okay. Luckily, we don't have to do that right now. So let me go ahead and erase this first. Okay, so now that we reviewed that, let's go back into the notes we've been talking about. That's not it. I want... avert your eyes. There we go. I forgot to erase it for the last period. There you go. Okay, so we are on example 5 of our notes. Converging or diverging sequences. Determine whether the sequences converge or diverge. If it converges, give the limit. Okay. So a couple of these go ahead and provide an expression that would give me a way to go ahead and find out, if it converges or diverges. But like B and C, we're going to have to come up with an expression on our own. Now these here in the beginning, these can get really, really complicated, but we're just, starting out with basics. I'm just introducing this to you. So just based on the pattern that you see, hopefully you can create an expression that'll model that. Okay, so let's start with A. 1 over 1, 1/2, 1/3, 1/4. Well, you'll notice the only thing changing, the denominator is just increasing by 1, so we have 1 over n. Okay, 1 over n would represent that sequence. It would go ahead and give me any term number in it that I want. Okay, and in fact, does it look familiar? What if I just replaced n with x? We know 1 over x is what? It's the rational parent. That's exactly right. Okay. So here's the thing. Think about it in terms of the rational function, what we were just doing on the focus activity. Do they have the same degrees, or is one larger? Oh, they don't have the same. Remember, a numerical value is not said to have a degree, only variables. So there's no degree up top, but what's the degree of the denominator? 1, because it has a power of 1, right? So this means that the denominator's degree is larger, so what case is that? Is it a slant? Is it a specific number? Or is it the x-axis? It's the x-axis. If the denominator's degree is larger. So what I can say here, the limit as n approaches infinity of 1 over n, well, it's the x-axis, so it should just be 0. And just think about the graph. 1 over x, 1 over n. You remember the rational parent's going to look like this. We have a branch here. We have a branch here. So think about the number of the term being the x value. So we have the first term, second term, third term, fourth, and so on, right? So the y value is the term itself. So think about you're just getting these points as you go further along. So you'll notice as x gets bigger, it is getting closer to what? The x-axis, 0. So the limit does exist. We are approaching a specific number. So what would you say? Does it diverge or does it converge? This one converges. Okay, there is a limit, so it converges. Now let's try B. So look at the pattern here. Look how the numerator changes with respect to the denominator. We have 2 over 1, 3 over 2, 4 over 3, 5 over 4. So what would the next term be? 6 over 5. There we go. And then it would just continue like that. What I want you to do, take about, 15, 20 seconds, write out an expression with n that would model this. Just like with a, we had 1 over n, right? So write out an expression that would help me find any term I want in that sequence. So let's see if we can all get on the same page there. And it is going to be a rational function. Okay. Anybody think they have an expression that'll work? Okay, Connor, what do you think? That's exactly what I came up with. Okay, so n plus 1 over n. If you'll notice, the numerator is always exactly one value larger than the denominator. Did anybody come up with anything different? Okay. If not, that's okay. There was another one that second period came up with, but if you didn't come up with it, then I'm not going to worry showing it to you. But there actually would be another one that would work. Okay, so n plus 1 over n. All right, so we have another rational function. Well, there you go. Okay, you just have to give one restriction. It's got to be greater than or equal to 2. Because if you plugged in 1, it becomes undefined. So very good, very good. Did anybody else come up with that one? Good, good, good. Either one would actually work. So now that you mentioned it, I'll go ahead and write it out. So n over n minus 1, again, we would just have to say n's got to be greater than or equal to 2. Now, in fact, either one, doesn't matter which one you go with, what do you notice about the degrees? They're the same. Remember, what do we do if they're the same? We divide the leading coefficients. So this limit, as n approaches infinity, of n plus 1 over n, what would it equal? 1. We're just using the idea of the horizontal or that slant asymptote. Because the limit exists, because we have a value that it approaches, does it converge or diverge? It converges. There you go. Okay. We'll see. 2, 4, 6, 8. Who do we appreciate? It's just kind of natural that you want to do that, right?
Yeah.
Few people. Okay, Raphael is shaking his head no. So I was going to say appreciate Raphael, but he said no. So okay. Sad day. Okay, but anyways, this one does not give me an expression. What do you think the next term would be? 12, 14, 16. It's just going to keep going, right? So what little expression can help me here? I'm sorry? Oh, now we're not, this isn't arithmetic. Okay, this is, well, actually, I thought, my thought was 2n, but n plus 2, the first term, no, because that wouldn't work. Now, n plus 2, they are 2 apart, but like if you plug in 1, the 1 plus 2 would give you 3, which doesn't belong to the sequence. Okay, so this one is geometric. All right, so 2n would model any term that I'd want to find here. Okay, but this one's not a rational function, so we can't treat it like we've been doing the other problems, but what's going to keep happening? As n gets larger and larger, what's going to happen to 2n? Yeah, as n goes to infinity, 2n is going to go to infinity. Okay, so the limit as n goes to infinity of 2n is equal to infinity. As n becomes infinitely large, 2n is going to become infinitely large. So here, are we approaching a specific number? No, infinity does not represent a specific number, so this is the first one that what? Diverges. That's exactly right. Diverges. Okay. And let's try this last one here. Negative 1, 1, negative 1, 1, dot, 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 negative 1 to the n. Okay. And I've been kind of caught up on this today. It has nothing to do with math, but every time in my head I see the dot, dot, dot. Has anybody ever watched The Late Show with Stephen Colbert? Yeah. When he reads Trump's tweets, he always does the dot, 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 dot. I just keep hearing that in my head every time I do that. It's just real funny. Okay. Anyways, so what do we think about this one? It does provide the expression. Negative 1 to the n. What do you think? Will it approach a specific number? Will the limit exist? Okay. Who said no? Okay. That why?
Plug in stuff for n, I would suppose, because you plug in every even number you'll put it in, you'll just get positive.
Every even will give you a positive, and every odd will give you a negative. It's just going to be negative 1, 1, negative 1, 1 forever. So this sequence is not going to have a limit. It's just going to oscillate forever. So what would I say about it? Does it approach a specific number? No. Now see, it just bounces between negative 1 and 1, but it can only approach one number. So this one diverges. Okay, the sequence has no limit. Okay. So how are we doing on this idea? Is anybody confused by what we've been doing? Okay. All right. Well, let me make sure to go ahead and erase this bless you this time. So 8th period, won't have to worry about that. Okay, now let's go back and finally talk about some geometric sequences. We'll get the formulas and we'll go ahead and do some problems. And in fact, we should only have a little bit left of the notes. Tomorrow we'll take our quiz, which will be the majority of the period. But then it's looking like Friday, you should have pretty much the entire period to work on the assignment. Okay, probably do a couple problems together, just let you guys turn loose. All right, geometric sequences have common ratios. Remember, that was the value that we multiplied the previous term by over and over again. And we use the variable r to describe it. And when we were talking about an arithmetic sequence, we were always adding to get the next term, right? So we subtracted in order to figure out the common difference. So we use the opposite operation. Well, here we're doing the same thing. If you're multiplying to generate the sequence, well, then we would divide to figure out what the common ratio is. And you just divide consecutive terms. The second divided by the first, the third divided by the second, and that's the key. You have to divide by the previous term. Okay, you don't take the previous and divide it by the one that follows it. Okay, well, this general form here, that's the explicit. Okay, so the nth term of the sequence is equal to, what's a sub 1? What term number is that? That's the first times r, that common ratio to the n minus 1. In fact, that looks really similar to what function you looked at in Algebra 2. It's the inverse of a log. Somebody said it, I haven't heard it yet. It starts with an E. Oh, I heard somebody say it, exponential. Exponential functions, they're going to have a lot in common with those. Okay. Now, the recursive formula, what you're going to want to do every time you write the recursive formula, you want to give two additional pieces of information. You always, always, always want to give the first term, and then you want to make sure to put the restriction. Okay, here's just the general form, so I don't need to worry about the first term. So the nth term of a geometric sequence, I'm going to take the common ratio r and multiply it by the previous term. So a sub n minus 1. And our restriction is that n's got to be greater than or equal to 2. Okay. All right. Now, the nice thing here, unlike arithmetic, there's not going to be anything to simplify in order to get to, say, a linear function. It's pretty much going to be exactly what you see after you plug in your values. Okay, well, let's try a problem here. I believe it's number 6. This is our first one that is geometric, that we're actually using those formulas. Okay, so we want to do 4 things. We want to find the common ratio, the 10th term, a recursive rule for the nth term, and an explicit rule. Okay. All right, well, let's start by finding r. How do we do that? How do we find r if I know it's geometric? Okay, we divide consecutive numbers. So I could say the second divided by the first, 12 over 6, 24 over 12. And again, I'm just showing you that consecutive pairs, if it's geometric, should always give you the same value. So I know that my common ratio has to be 2. Okay, so that's easy enough. Now, the second one, the 10th term, so a sub 10, remember that little subscript is the term number, that's n, equals the first times r to the n minus 1. Now, when you write your explicit rule, you're going to notice that these two right here are virtually identical. Once you plug in, I mean, you've got the explicit. So the 10th term equals, now the first is 3 times the common ratio, we just found that to be 2. N minus 1 would be 10 minus 1. Again, I'm just showing you all the substitution. And so I don't have to write it again. We know the 10 minus 1 is just 9. And now it's just a matter of figuring out what that value is. What is 2 to the 9th tripled? 1,536. 1,536. There we go. Was that Raphael who gave that to me? Okay, so I will go ahead and do it. 2, 4, 6, 8. Who do we appreciate? Well, I'd say Raphael. I like how everybody was like, Raphael. Reminds me of that Monty Python and the Holy Grail. Has anybody ever seen that? And the peasants rejoiced. Yay. All right. Recursive rule. Okay. So again, when you're writing a recursive formula, you just want to make sure to include the first term. So we know the first term is 3. So a sub 1 is equal to 3. So to find the nth term, what was the common ratio? 2. I'm going to multiply that by the previous term. So a sub n minus 1. And am I forgetting anything? There is something I'm forgetting. N has to be greater than or equal to 2. Don't forget that restriction. There we go. Okay, there's the recursive rule. Okay. And finally, our explicit. This is the one that allows me to jump to any term that I want. It's not dependent on the previous term like the recursive is. So a sub n, the nth term. Can anybody go ahead and give that to me? What was the first term? 3 times 2, that was my common ratio, to the n minus 1. There we go. That was the explicit. See, there's nothing to simplify. I mean, really, the more work you'll be doing is if you're looking for the number of terms, which we're actually going to be doing in the series lesson, and probably bring some logarithms back in that. But any questions on what I did here? All right, are you ready for one on your own? Okay, so here is our sequence, and of course this one's going to continue. Okay, so 12, negative 6, 3, negative 3 halves, 3 fourths, dot, 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 dot. Sorry, I'm going to be doing that all day. It's just funny to me because he's a horrible person. Good. No, Stephen Colbert is actually really funny. I was talking about Trump. I mean, again, not meaning to step on anybody's toes. If you're a Trump supporter, there you go. I mean, I don't know what to say about it, but, you know, this is America. You have the right to be wrong. Okay. Okay. Bringing a little bit of real life into mathematics. I think that's what we're doing here. Okay. I mean, it's your country. I mean, you guys are going to be inheriting it in the next decade or so as you move into college and the workforce, and you're definitely going to be affected by what's happening. So, come on, next November. That's all I can see. Not this November, November 2020, when hopefully we vote him out of office. Okay, anyway. But then again, I mean, he didn't even win the popular vote. He was still voted in. Thank you, Electoral College. But that's something else. Okay. All right, I'm going to go ahead and give you 2 minutes. Okay. 2 minutes. Try this on your own. Find me the common ratio, the 10th term, a recursive rule, and an explicit rule. And at the end of 2 minutes, let's see if we can get somebody up here to help me out with this. Okay. Okay, that is 2 minutes. Would anybody like to come on up and show me what they got? Hey, there we go. Okay. Come on up, Dylan. Dylan's going to help us out with this. You don't have to unless you want to. I only did that because I just wanted to, emphasize that any two consecutive terms would give you the same common ratio. Okay, so it is negative 1/2, and it is perfectly fine that the common ratio be negative. There's nothing wrong with that. Okay, so the 10th term, the first 12 times the common ratio, negative 1/2. I'm sorry, sir?
It's oddly proportioned to A.
Okay.
That's cool, I guess.
There was that better.
Really, it looks about the same size to me. Oh, okay. 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 So negative 1/2 to the 9th is a negative 1/5/12, and that would become negative 3 1/28. Perfect. How are we doing so far? Good. Okay. So the recursive rule, he did provide the first term. Good. So the nth term would be negative 1/2 times the previous. Okay. And we have our restriction. N's got to be greater than or equal to 2. Perfect. That is the explicit. Everything's perfect. Anybody having a hard time? Anybody not get those? Is there anything I can do? Okay. Well, we have the one problem left that we can take care of tomorrow. Remember, you have your quiz, and then Friday we should be able to look at the homework. Okay. Good, good, good. Yes. Honestly, in years past, I've usually voted Republican, but I've got to say, in the past couple of years, I'm really ashamed of how a lot of these Republicans are acting. So I would probably say I'm leaning more towards Democratic now. But I mean, the two-party system, I've never been a big, I don't know. Just, I don't know if this is how the founding fathers envisioned the country becoming. Yeah. True, true, but I don't know. Yes, sir.